Well, good afternoon and good morning, everyone. I am Steve Murphy, and I am your moderator, presenter, everything here today. Um, let's see, I just want to make sure one thing before we get rolling. Want to make sure I'm heard. Yes, good. Do that. So again, well, thank you for attending. We appreciate your time in attending. This is a coffee break. And so if you've got your coffee break, if you've got your coffee handy or whatever you choose to be drinking at this time of day, then feel free to grab it and we'll begin. This is one of a series. And we're going to be holding those every last Thursday of the month, and they're scheduled to be around 30 to 40 minutes. So I'll try to keep to that time frame. And it's really about getting the most from your oscilloscope for both debugging and validating circuits performance. And I'm going to try to keep this generic for not a specific scope, but hopefully I can keep to that. So this first one is about getting your oscilloscope set up correctly. And you can see there's a number of different topics that we'll be covering within each month. And we'll start more around the scope, but then we're going to move into applications, and we'll continue this throughout the year. This is me. I'm an applications engineer, and I've been here about 25 years, and actually more than that, and then also with a competitor, and been in the business, been in the oscilloscope world for quite some time. So I'll try to make use of that in providing you a quality and good content here. This first part one of the Coffee Break webinar series is we're going to focus on the scope's vertical and time base and a little bit on the trigger setups, because we want to make sure that the scope is doing and is set up for exactly what we want it to do. The way that I'll go through this here is I'm now in the intro and setting the stage, but then we're going to move over into the details of analog bandwidth and do we have enough of the signal. We'll look at the interaction of a scope's time base, the time window, the capture time, the sample rate, the memory length, and how all of this is going to affect the digital bandwidth, so very important, and how they interact. And then we'll look at the ADC and the vertical resolution that scopes provide and when and why do you need it. And then we'll look at briefly at triggering. And I'll take questions at the end, and there I'll keep an eye on the as much as I can the panel there. So I'll try to keep track of the question panel. Feel free to put your questions in there, and also there will be, this presentation will be sent out to you as well, and it'll be posted. My webinar presentation PowerPoints will be sent out and available to you. So that's where we are heading. Let's continue on now. All right, more on setting the stage. To begin here, this is on digital storage oscilloscopes. There are some banner specs that I'm highlighting, and this is actually a scope that I have on my desk right now. All scopes have analog bandwidth. All scopes are specified with their maximum sample rate. They're also maximum memory, and there's also the dynamic range. What is the ADC? And is it 10, 8, 12 bits within the scope? Now, this is the scope that I have, and why don't I just do this? You will see me, let's do it this way. You're gonna see me, like, not too much, but here I am, and you will see me bounce between my webcam, and this is the oscilloscope that I'm using. It's Windows-based, right? So it's running Microsoft Office, and so PowerPoint is going to be run here. I'm tied into the browser to go to webinar, and I'm going to do everything from this oscilloscope here today. And what else do I have here? To show off some of these things or to discuss these topics, I also have on my bench, here's my coffee, but I also have a signal generator here that'll go up to 3.5 gigahertz. And so we want to take a look at that, and we're going to feed that to our 2 gigahertz scope. By the way, this is this particular oscilloscope is got 12 in front end, 12 bits of dynamic range on every one of those channels. And but again, that's what I'm using here today. And so let's dive into that a little bit more. Here is a block diagram very briefly, right? So we have our analog input, and many times we'll use probe, single-ended or differential to get to the right level. But and this is the B and C of the scope, and that amplifier amplifies, but it also attenuates the volts per div or current per div, so that the ADC gets the right amplitude. So that's the purpose here. Then, of course, we have a sample and hold that's not shown, but we also have the ADC that is converts the voltage or current coming in and converts it to a digital value and holds it, and it follows the quantization level by that ADC. And then we have memory that stores all of those data points as they're converted to numeric values internally in memory. And then there'll be some post-processing as well and display. And of course, we have the trigger circuit who gets a piece from the amplifier here, and it has its own bandwidth as well, by the way, and it helps us to, with the source that we've selected, to get a nice stable display and define where in the waveform, where in the electrical signal we want to focus our reference point. So that's just the general block diagram. We'll use this as we go through. And now let's focus on the analog bandwidth. A little coffee here. Okay, so do we have enough signal? And as we use scopes, right, there are different, the specs we talked about, but this front end amplifier has a bandwidth, and we always like to try to push the limit, I think, on our oscilloscopes as circuits get faster and faster. But where do we start hitting? Do we hit a brick wall? How does the analog bandwidth, how is it specified? And are we reaching limits as our circuits get faster? So this is scope bandwidth. It's the analog bandwidth, but it's also the digital bandwidth, which I will hold as a separate topic. So on analog bandwidth, we know, right, that if we look at the amplitude of a signal that we're acquiring through the front end BNC, and as we look at the frequency response of that amplifier, and this is true of all scopes, right? If you put a 1 volt in and DC, yep, you'll get 1 volt displayed. But as that signal increases, of course, we know that there is a roll-off and there is a filter, and that has some performance, right? So when we reach 3 dB down, or 0.707 of its amplitude, that is where scopes are specified at that 3 dB point, or 70% of the actual 1 volt amplitude. So that will give us a lower amplitude. We'll see the signal fine, and the trigger circuit will be fine, but we'll have a roll off. And so how this rolls off too is also a subject here for today, because you do still have frequencies that are out here beyond the bandwidth of the scope, and so these will also contribute to your displayed captured waveform. So as an example here, just to confirm this, I have a 3 gigahertz scope, and in this case, if you will, just for this example, and I have a 1 gigahertz sine wave. And then what's the result going to be as I increase that to up to 3 gig? You're going to see the amplitude drop to follow that 3 dB point. And how it drops too. What is this response here? Is it flat? Is it a single pole roll off, or is it multi-pole? Well, let's take a look at that, and let's go live right now. So back to the oscilloscope and back to our generator. Now let's go to the oscilloscope software, and I'm looking at this is an MDA 8000. It's a 2 gig scope. It's a 12-bit scope, of course, with 8 channels. But I am live right now, and this is my generator. Let's just go to this. And so I have, I'm controlling the generator, the oscilloscope, and what is our frequency here? So what I did is I added a table for this. I right now in P3 in the table of parameters, I have 1.5 gig is what I am outputting right now. I've asked for the generator generate about 1 volt peak to peak, which is, you know, plus or minus 500 millivolts. So what's going to happen? So I've got this. Put this over here. I got the generator. I've already set up the amplitude to get us this 1 volt. But now let's go ahead. Let's change the frequency. And so I'm at 1500 megahertz, 1.5 gig. And you can do this on any scope, right? Just as long as you have the source. All right, and I will go a little faster. Okay. Okay, this is what we've got now. We are at, what are we at? Let's hit clear sweeps. Let's look at the readout on the scope. We're at about 1.7. Let's turn on statistics so I can see what's going on here and make it better. And then so we are now at 1.8 gigahertz is our sine wave. Watch what happens here. What are we at now? Let's do clear sweeps. We're at 2 gigahertz right now. And we're still just about where our peak to peak is just still about 1 volt and just about 5.5 millivolts. So we're doing good with this this 2 gig scope with a 2 gig sine wave. Actually, it actually should drop, and we're starting to see it now. Let me increase this a little bit more. We're now at, oh, you can see it dropping now. We can see that at 2.1 gigahertz, our amplitude now is 670 millivolts. And of course, peak would be 336 millivolts. So we are dropping. You can see that on the display, and I'll keep it going. Let's go to 22.2 gig. There, our signal is really starting to drop off. And so the amplitude now is much lower. We still see the waveform. We're still triggered on it. My trigger level is up to the top right here. But there's our signal. And so our 2 gig scope, we're pushing it. And I could change the amplitude on the amplifier too, by the way, right? So here's 2.3 gig. Let's close that. I could change the sensitivity if we wanted to. So we can see the oh, there we go. So we can still see the amplitude, but it's getting tough. So that's the roll-off that all scopes are faced with. Okay, and so if we go back to the slide here, and I like just using this one, it's clear here. So we could see that at 2 gig, when we were specified, the scope actually gave us higher voltage, so it actually rolled off further out, which was nice. And then it did out here at 2.1, 2.2 gigahertz signal. The amplitude really started falling off, and you could see it till it was very small on the signal. And that's what scopes do. So if the content of your waveform has high frequency, you want to be, this is what happens to the frequency content. It will attenuate the higher frequencies at this rate. So what do? We always like to get a recommended bandwidth that takes into account this roll-off. So you want 2 to 3 times the bandwidth of the scope to the maximum frequency you have in your signal. And there's a little formula here that correlates it to rise times, and this scope here, I believe, is in the 175 picosecond rise time area as a 2 gig scope. So at any rate, that's the frequency I would be able to measure on signals. But most important, back to the amplitude versus frequency roll off. You know, get scope that has higher frequency. If you're not pushing the limits of the scope of the content, the frequency content of your signal, no problem. If you don't care about the amplitude accuracy, you just want to see a signal, then also you don't need to be, this is not an issue as much, right? Just be aware that you're going to see a signal, but not the appropriate accurate amplitude. So you're the scope users, you decide what's good. So for the purpose of why you're using the oscilloscopes. Just going to do a quick little check here. Good. All right. So let's see. Now let's move on to effective digital bandwidth, and so important. And I see customers that I work with forgetting about that. So let's just do a quick little reminder here. There is this thing called effective digital bandwidth, and that is good old Nyquist says I got to take at least 2 samples on the waveform in order to understand what its frequency content is. And of course, more is better. So therefore, the sample rate is the speed at which the scope digitizes and records the voltage level. And then the digital bandwidth is half of that due to Dr. Nyquist. And then now most important here is memory length. That can limit your sample rate and at certain times, therefore it will affect your digital bandwidth. And so there is this little formula here that if you look at your time base, your time per div, that is usually a times 10 gradical. So whatever that time window is, so time per div times 10 divisions would be your total capture time. And if you look at your memory length, these two define that ratio, the sample rate. So you either have to reduce your capture time to maintain your sample rate and therefore maintain your digital bandwidth, or you have to increase your memory. And that is very important to do it. Here is an example of the top is a simple sine wave. It is a narrow band, of course, because it's just a simple sine wave. And here we're going to want to have at least 2 samples, right? And here I got 4, but we want 2 samples per cycle. Nyquist says that's the case. But when you have broadband, where you have edges that have more frequency in it, faster rise time and fall times, maybe even some overshoot, which is even higher frequency. So nonetheless, we do have broadband requires our sampling to be faster. Realistically, when you're pushing the limit of a scope, like trying to get the most bandwidth out of the scope, then you're gonna typically have at least 2 to 4 times oversampling on that signal is what it ends up at the end of the day when you're really working to get the most out of your scope with the highest frequencies possible. Digitizing is so important. I think what we could do is, well, here's the memory, and so my point has already been made that, but I'll just show you this one thing. Imagine, well, how memory is going to affect your sample rate, what affects your digital bandwidth, right? So here on the top, we are looking at nice waveform, and it's captured appropriately with the right time window. But if you don't have enough memory and you want to maintain the sample rate, you're going to have a less time window. That's all there is to it. Otherwise, if you try to maintain your time window and you only have that limited number of samples, then of course, remember, right? You're gonna have to drop your sample rate since you don't have the memory to back it up. Same thing here. What if you have a glitch? Well, it's caught nicely here in the top, but if you have limited memory, then you either keep your time window short, while you reduce your time window to maintain the sample rate, to maintain your digital bandwidth, or you spread out your time window for the amount of memory that you have, and your sample rate drops, and of course your digital bandwidth drops, and therefore that little glitch right there, it's not going to be seen in either case. So memory is so important on scope. Just keep an eye when you go to, let me just do this. When you go to your scope, right, here in the time base, there's a waveform descriptor, at least for the LaCroix, where it will tell you what the sample rate is. And we will also tell you, and you have a choice. You can be memory priority or sample rate priority. I'm a sample rate guy. I like setting my sample rate because it tells me what my Nyquist bandwidth is, what my effective digital bandwidth is, and then the scope will add or subtract memory. For example, I am right now, let's clear sweeps. I'm at 2.1 gig. Let's just drop that. Well, I'll just drop it. Let's just drop it down to 1.5. Clear the sweeps. Of course, I changed the sensitivity, right? And okay, now we have a good signal. So if I want a wider time window, we're going to vary that, right? And let's just do this as much as I can. We're going to vary this. Oh, that's in the way. Forget it. And so that's 10 gigasamples. We're using 5,000 waveform, 5,000 sample points. But as we go for a wider time window, now 200 nanoseconds per div times 2 times 10 divisions. So we're at 2 microseconds now. We're going to need 20,000 points to maintain that sample rate. So you get the idea. Very important to watch these. As you have more and more data, your priority, maybe you want to say, hey, I want to go to set my maximum memory. When you do that, I mean, that's all bets are off. So I'm really, you can see I'm aliasing, I'm not capturing the signal. So at any rate, there is, that is the relationship. And hey, let's just look at that. Let's look at that waveform. And we're at 50 samples. Let's stop it. Let's go single. You can see, I closed this. It's comprised of digital data points, right? As we reduce the sample rate, you're going to see, let's go normal again. As we do reduce the memory or reduce the sample rate, here we're at 50. Well, I'll just go with sample rate right now. Oh, wow. You can see we are only capturing only a little. So it looks like a nice sine wave, right? But it really is, we have connect the dots turned on as our default. And so we will build up a waveform here, but it's so important to understand that how much sampling, what's our sample rate, what's the time point divisions, and this, excuse me, this right now we are at 500 picoseconds per division on the main trace. We're sampling at 5 gigasamples per second. We're using, in this case, only 25 samples. And that means that 5 gigasamples per second, 200 picoseconds per point, and our total time window with 10 divisions is 5 nanoseconds. So anyway, the scopes will all give you this detail for you to help you understand what your Nyquist or what your Nyquist and effective digital bandwidth is. 5 gigasamples means I'm at 2.5 gigahertz here, and on my 2 gig scope. So I'm more limited by the oscilloscope's amplifier than I am with the sampling, which is a good thing. So anyway, those are different topics. I'm trying to cover it quickly. I apologize. There's maybe a little faster way to do that, but how are we doing on time? It's going good. All right, so let's go back now, and I'm gonna also just check for any questions? Nope, okay, we're good. And let's move on. So now, so that's the analog and effective digital bandwidth. Now let's go into resolution, vertical resolution, and what we're really going to be focused on is what is our interest, what is our requirements on our measurement to see small signals buried in larger signals, and what is our requirement, our goal of using the scope for accuracy. So those are the two things that I'll focus on here today. Of course, there is our ADC, and this all oscilloscopes have hardware ADCs. There are many times they're supported with post-processing to get higher effective number of bits, but we are now basically going to use that ADC with the sample and hold, and we're going to, using the number of ADC bits and quantization levels, we're going to create and store all the voltage values in this case and convert them to a number. And higher resolution, so most scopes have 8 bits, right, for our multi megahertz and even gigahertz scopes. Lower bandwidths have higher dynamic range, higher frequencies have less. So we have, this will show the details. And so I kind of played with this before I started this presentation here today. But so let me show you this. So if we have an 8-bit scope and a 12-bit scope as a comparison, 2 to the 8th means that when you sample a scope, a waveform, you have 256 choices, or you have 4,000 choices, depending on your ADC. And therefore, there's also a dynamic range here listed as, and I think of this too as many times equating that to the frequency noise floor of the FFT. But anyway, 48 and 72 dB is the dynamic range. So when you're looking at a waveform and you've either got to put this sample point up here or down here when you define that value. So you have 2 choices, but you can see I took just a small piece of it, but you can see it's wider compared to a 12-bit scope with high resolution. So lots more, 16 times more dynamic range with a 12-bit scope. And a lot of us manufacturers now have those. LaCroix's on its 3rd generation. And by the way, they go up to 8 gigahertz now, which is pretty amazing. But also to point out is when you look for details, so much better to do that with more dynamic range. And if you're trying to get good measurement accuracies, keep an eye out on the DC gain accuracy. You'll see that we go from 1.5 or 2%, depending on the scope, and the manufacturer is up to 0.5% with a 12-bit scope. So that also is a consideration on which scope you should purchase for the future. Here is a 12-bit versus an 8-bit. And let's just go back to the scope now. I'm going to go back over to here. I'm going to select the scope, and then you're going to watch me go up to File. I'm going to recall the lab notebook, and I'm going to do pretty much regenerate that slide. Here's the coffee break. Let's go do this. I just want the single one right now. I wonder if that's going to be there. So what I've got coming up is I'm using Lab Notebook, which stores all the waveform data, the panel setup, even an image it's stored with it as a single push button. But I'm wanting to compare 12 bits to 8-bit dynamic range with you. And so this top waveform is a current pulse. It's from a motor drive application, so the motor is pulling current. And we weren't quite sure how to set the amplitude. So because we wanted to make sure we got it and got everything and the amplitudes were correct, and indeed, boom, we got it. We got it this time, which is great. And then what we did is we created 3 zooms. When you're trying to see the frequency content of here, this is a zoom of that part in yellow. You can see in blue, it's this part of the waveform as well. And here you can see the details of this down in this zoom. All of these zooms, by the way, just using the scope, you can, well, it's already open. Let's see, you can vary their amplitudes and time window and all that stuff individually or together. But what happens, let's see if this waveform has it. Let's go to, I'm gonna call up, let's go to memory. Let's see if they're here. Can I do it? Yes, yes. This is an 8-bit scope on the right, so I want to compare dynamic range for you. Again, we're trying to find the small details in signals. Maybe it's ripple, maybe it's this type of signal, and we want to see the details, make measurements, and then accuracy, again, was the other point that I was making. So you can see the noise on an 8-bit is significantly higher, significantly higher. This one is a zoom of the 8-bit. Look, that's looking better than I would have thought, frankly. I would just, I would flash back this, but nonetheless, you get the point. 256 choices versus 4,000 choices is significant and helps you with your measurements and will also give you the accuracy. Okay, again, I'm trying to move fast. I have love to talk to you guys more afterwards. We have a whole set of applications engineers and sales engineers that can have these discussions with you, but I'll give you my contact at the end here too. So in triggering, just a quick one. We're going to do a whole 30-minute segment on this, a coffee break on that, but here we go. This is the trigger. It has its own bandwidth that's defined, especially on the higher bandwidths. We're more attentive to that, the higher bandwidth scopes, but it basically tells the scope where it needs to, what's going to hold the pre-trigger information and filling up the post-trigger information. So it synchronizes where on the waveform we want to focus our attention. And there is many times I get, on a scope like this. Let's go to back to the scope for a second. Let's go to File. I know I've got to wrap up here, so just give me another minute. Let me go recall another lab notebook. Let's go to do have it. Should be here. Maybe not. Maybe not. Nope. So let's just go to close, and I'm just going to set factory default and go to channel 4 and shut off everything else. And actually, I'm showing it now. If there are oscilloscopes, to make my point, oscilloscopes have these things called auto, normal, and single shot triggering. And the scopes trigger circuit, and they're called different things with scopes too. There's run and stop, and there is, if you're in run, you can, I think there's a setup for you to choose whether you want auto or normal. And let me just point out that normal will only update the waveform display when there's a trigger, when there's a valid trigger, whether it's an edge or pulse width or whatever you've done. Auto trigger will say, oh, I'm going to try to find that trigger point, but if it's not there, I'm just going to keep updating and giving you a display. And again, try to trigger, but it's going to be a continuous update. And of course, single shot is just a single. These are your sources, of course. But I was just pointing out on the scope, which I guess is going to be just fine. I can see right now that I have channel 3 and channel 4 turned on. And as I change things here, I can see there's something going on channel 4. I bet you if I turn on channel 1, let's go turn on channel 1 in the front, and we speed things up. We have to go to 50 ohms. Anyway, there is, there's our sine wave. So imagine if I didn't have a valid trigger, I would get this, which would be, let's put our trigger on 3. Let's move trigger over to trigger. And then right now everything is stopped. So I really can't see what I'm doing. This is just a quick reminder. Don't forget about auto trigger, where you can attach your probes. You can see what the signal, if there's any of the signal there, you can set your volts per division. You can set your time per division. And it's much easier to do that when you have a trigger mode called auto and normal. And of course, there's always a single shot. So there's so much more we could be covering. Just as a close, and I will open it up for some questions. Let's see, let me push this off here. And so again, we covered the analog bandwidth. We covered that dynamic range, how important that is to view small signals in larger and completes the accuracy. And then I think about metrology, right? Where you think about, hey, you're trying to use precision equipment to make measurements on other products or signals. And same thing with the scope. Make sure that you have the precision that you want from what you're trying to measure. So use a scope with the right bandwidth. Remember the 3 to 5 times more bandwidth rule if you're focused on amplitudes, and that's important. We'll think about more vertical resolution for looking at 0.5% DC gain accuracy. And what is it that you're trying to measure? So anyway, these all need to be thought about, and what is the purpose of your measurement? What are you working with? What's the situational awareness? And then get the right product to help you do that. Just as reminders, waveform memory supports maintaining the appropriate sample rate, which directly affects your digital bandwidth. Don't forget about that. And so we're off over here. This is going to be recorded and available on our website, right? So on demand. And don't forget the software that I'm using right now on the scope. You can download that and apply for the license, which you'll get immediately when you do that. And then it'll turn on all these options that you saw. Well, I really haven't spent much time with today, but anyway, know that the oscilloscope software is there, and it's really an offline scope that uses, lab notebook files and stored waveforms and traces. So really want to thank you for your attendance. I'll now take some questions. We went pretty good on time. And okay, so let me just read them for a sec here. The trade-off between memory depth and as it relates to the window. That is really, when we look at the scope, and let's just go to normal. And I'm gonna flick off this other stuff right now, although it is pretty good right there. Let me do this. And then I'm gonna also trigger on channel 4, and I'm going to trigger on to answer that question, by the way, is where I'm heading. So give me just a sec. So on the trigger, I want to trigger on 4. I want to trigger on a width less than 200 nanoseconds. I have to keep moving this thing out of my way. Nano, okay. And then I'm going to set my trigger level on the right. You can see it on the right. Excuse me. And I'm going to turn up the time base, go to normal trigger. This is a pulse width modulated signal. Close. And now if I am memory priority, and let's go to 1 megasamples per second. And I'm going to move this question panel on the side here. And let's shut off channel 1. I'm going to flick it off, go to display auto grid. Let's just go to single grid, actually. I've got to do something else, but anyway, so you can see I'm triggered right here. There's a glitch. I happen to know that, but look at the quality of that glitch now. If I reduce my memory, I'm pretty zoomed in on it right now. As I reduce my memory for this time window, then, or I'll just do it this way, and let's do a zoom of it. Look at that glitch and how it's actually being caught. It's being caught at 2.5 milliseconds per division for 500 samples at 20 microseconds per div. That's 200 microseconds. If I touch my my channel and slow this down, oh wow, and that glitch is just disappearing. Why? Because I must slow down my sample rate for that wider time window, which is now 100 microseconds per div times 10. And so now that's 1 millisecond per div. That glitch is gone. The trigger circuit is actually catching it. But you can see there's no details on that. Why? Because of the wider time window. If I bring the time base closer in, where I can get now I'm much faster, much narrower time window at 2 microseconds per diff, so 20 microseconds. Now my sample rate with that limited memory can go up because I don't need it for the time window. And now my glitch is being seen in details and I can make some measurements. So there's a relationship here between the time window, the memory length for that, and therefore the sample rate, which hits us right on the digital bandwidth. So I'm 50 megasamples per second, and now we're at 25 megahertz effective digital bandwidth. Even though I have a 2 gigahertz analog scope, we're not going to see that because the sample rate is so slow. But that's the relationship to answer your question. How does the 1x and times 10 probes play into your attenuation? Yes, it does. On the front end, if I go into the PowerPoint, where are we here? I guess really at the beginning here. What we're trying to do here is get the right signal into the amplifier in the BNC. If it's really large, we got to attenuate it. Therefore, otherwise the amp can't handle it. It depends also whether we're 50 ohm or 1 mega ohm input impedance as well. So, but nonetheless, if we have a large signal, we've got to reduce it so the amplifier can take it, and then from there we'll attenuate and amplify as needed for it to get it in front of the ADC. If we have a small signal, then a divide by 1 or times 1 probe is going to be helpful, and therefore we'll get, again, the right amplitude into the BNC so that the amplifier, the scope, can deal with it. So that's how it plays in. It's just getting the right signal level at the start to the BNC of the scope. I think that's pretty much it. I'm way off of, well, I'm at my 42-minute mark. I hope this was helpful. We really appreciate you attending. At the very end here, I think I had, yep, my contact info here, just a sec, yep. And let's show that. So this is how to reach me. And of course, we have sales engineers and applications engineers, factory folks, field folks, all here to support you. Again, we're going to do this every month. We'll pick a different topic. Stay tuned. We'll get the details of this presentation to you. And again, ask questions afterwards, no problem. And we look forward to having you attend our next webinar. Everyone, take care now. Be safe.